By the way, you'll see in graph literature that the way we generally denote a graph is usually by the capital letter G, and it's written as an ordered pair V comma E, where V is the set of all vertices and E is the set of all edges. Now what do we get if we took the sum of the degrees of all the vertices in an undirected graph? You can pause the video and think about which of these four choices is the correct one, and then we can proceed further. So let's take a simple undirected graph here. How would we add up the degrees of all the vertices? Well, we can do that for each vertex here. Let's start from this one. This vertex has a degree of 2 because there are two edges out of it. This vertex also has a degree of 2, so let's add 2. This vertex has a degree of 3, the 3 edges linking to it, and this vertex has a degree of 1, so I just put a single mark here. Now if we add up the degrees of all the vertices in this graph, notice that each edge would be counted twice, once for each of its endpoints. So when we add up the degrees of all the vertices in an undirected graph, the answer is going to be twice the number of edges. This is an important result that we will keep encountering all through our study of graph algorithms. Now, what if we ask the same question about directed graphs? In case of directed graphs, let me just make a simple directed graph here. When we have directions on edges, we can't just talk about the degree of a single vertex because we need to distinguish between edges that are going out and edges that are coming in. So there are actually two notions of degrees in case of directed graph. There's something called an out degree, which is the number of edges that are going out of a vertex. That's the out degree of the vertex. And the in degree of a vertex is the number of edges that are coming into the vertex. So what do we get if we added the out degrees of all the vertices in a directed graph? Well, if we added all the out degrees for this simple graph, we would get a 1, 2, 3, and 4. There are 4 edges in this graph, and we also got a value of 4 for the sum of the out degrees, and that's because when we are adding up the out degrees, we are actually counting each edge once. We are counting each edge from the vertex where that edge starts from, not the vertex where it's going into. So the sum of the out degrees of all the vertices is just going to be the total number of edges in the graph. By the way, this absolute sign just refers to the size of this set of edges, which is nothing but the number of edges. And in a similar way, when we add up the in degrees of all the vertices in a directed graph, we are again going to get the number of edges in the graph, because when we are adding up the in degrees, each edge would be counted once for each vertex that it's leading into, right? So the in degree of this vertex is 1, the in degree of this vertex here is 1, the in degree of this vertex is 0, sorry, it's 1, because this is one edge that's coming into the vertex, and the in degree of this vertex is also a 1. So when we add up the in degrees here, we again get a value of 4, which is the number of edges. So the sum of the out degrees of all the vertices in a graph is equal to the sum of the in degrees of all the vertices in a graph, which is equal to the total number of edges. And this is the case for directed graphs. For undirected graphs, that sum is twice the number of edges. For directed graphs, that sum is split evenly between the out degrees and the in degrees, and each of them has a summation that's equaling the total number of edges in the graph. Now Euler said the same thing for undirected graphs in this language. Here's what he wrote. I observe that the numbers of bridges written next to the letters A, B, C, etc. together add up to twice the total number of bridges. Okay, so he's talking about undirected graphs here, since the map of the 7 bridges of Königsberg was an undirected graph. And the reason for this is that in the calculation where every bridge leading to a given vertex is counted, each edge is counted twice, once for each of the two vertices at its endpoints.